This is looking at an example of using the geometric distribution, very similar to the binomial distribution, except we don't have a fixed number of trials. With a geometric distribution, we keep going until we get our first success. And the example we started looking at in the lesson was of two pandas who had a 5% success rate every time they attempted to mate. 5% of times the female panda would become pregnant. And we said for a geometric probability, the key thing is the value of p. P is the probability of success. And in the example we're looking at now, 5% as a decimal is 0.05. So we would start our question off using any letter we like. A capital letter X would be maybe the number or the attempt which has the first success. So part A of the question was asking the probability that the first successful mating was on the third attempt. So there we're wanting X to be equal to 3. We said that as it follows a geometric distribution, which we write down like that, X, and that little squiggle, and then geo, in the bracket, it's only one thing that goes in here, it's the p value. So that's 0.05. We said the formula for the geometric distribution is failures, and the probability of failure is 1 minus p. Failures every single time apart from the final time. So it's 1 minus p to the power of r minus 1, and then times by p. That dot there is indicating you multiply those together. So for part A of the question, where it was working out the probability of the first successful matings on the third attempt, would be 1 minus p to the power of r minus 1 times by p. So I have the failure probability twice and then the success probability. And if you work that out, you get 0.0451. Part B of the question said, what is the probability that they will have to mate more than 8 times until they get a successful pregnancy? So that is probability that X is greater than 8. And we said, well, that will be then the probability they mate successfully on the 9th time, or the 10th time, or the 11th time, and for all these ors I'm adding up, and that actually can go on forever. It's what's called an infinite sum. It will go on forever and ever. But actually each probability will be smaller than the last one. So whilst we're adding on more and more numbers each time, each number we're adding on is actually getting smaller and smaller. But if you have one of these, let's look at these first 3 probabilities. The probability X is equal to 9. Well, according to the formula we had earlier, which is up here, that will be failure to the power of 8, and then times by your success. I'm not going to work it out as a number at the moment, I'm going to leave it like that. The next one, X is 10, will be failure 9 times in a row, followed by success. And I'm not going to work that one out. The next one, 11, would be failure 10 times in a row, times by success, and that will carry on that pattern. And we've got to then add up all of these values. Adding a set of infinite numbers up, you might think is impossible, but there's something you haven't yet studied in core maths which enables you to do this under certain circumstances. And as far as the geometric distribution is concerned, those circumstances will be true. There's a special formula. It's called the sum to infinity. I'm not going through any details now, it will be explained in core maths, I'm just going to give it to you. The sum to infinity is equal to a over 1 minus r. This r is different to the r that we've been using, for example, up here. This is an r from the geometric adding them up formula. The a at the top is the first term in your pattern. The first term in the pattern. The r stands for the common ratio. Now I'll explain what they mean by looking at our number pattern. And the number pattern I'm looking at is basically the value here, the value here, and the value here. And if you look at them, they are similar. They've all got this bracket in it with a power, and they've all got times by 0.05 at the end. In fact, to get from this value here to this value here, well, ask yourself, what do you do? That stays the same. This bit here is what changes. You're multiplying by another one of these. And that bracket has got a value of 0.95. So to get from the 9th bit to the 10th bit, you are timesing by 0.95. And to go from this line to this line here, again, you're timesing by an extra one of these. Instead of having 9 of those times together, here you've got 10 of them times together. So again, you're timesing by 0.95. And that 0.95 is this common ratio down here. In A, the first term in our pattern is this sum here. So if you've got to add up a whole infinite set of these numbers, you use this formula. A, the first term, is all of this. Well, I do know that that 1 minus bit is actually 0.95. So it's 0.95 to the 8 times by 0.05. That's the value of A, the first term in our pattern. And I divide it by 1 minus R. And R was whatever I'm timesing each line by to get the next line. And here that was 0.95. Now it so happens here that the answer to this little sum on the bottom is 0.05. I'll just write the top line in here as well. So you may have spotted what happens here is that they actually cancel out. And you are left with here 0.95 to the power of 8. And if you work that out on the calculator, you get 0.6634. And that's actually the answer to the question that we want. We've added up an infinite number. Again, that will be explained far more in your core, but if you can follow that for now, that's great. So the probability that the pandas will need more than 8 attempts to get pregnant is 0.6634, which is about 66%.